we're asked to use the method of Lagrange multipliers to find the points that represent the relative minimum and relative maximum for f of x comma y equals xy, subject to the constraint y equals 9 minus x squared. We will assume the conditions of Lagrange's theorem have been met, and therefore if f of x comma y has a max or min, subject to g of x comma y equals 0, then the gradient of f is equal to lambda times the gradient of g and g of x comma y equals 0, which results in the system of equations below that we need to solve for x, y, and lambda. To begin, we are given f of x comma y is equal to xy. To write the constraint g of x comma y equals 0, we need to set one side of the equation of y equals 9 minus x squared to 0. Let's go ahead and add x squared to both sides and also subtract 9, which gives us g of x comma y is equal to y plus x squared minus 9. And now let's work on setting up the first equation given by the partial of f with respect to x equals lambda times the partial of g with respect to x. To find the partial of f with respect to x, we differentiate xy with respect to x, treating y as a constant, which gives us 1 times y, or y. We have y equals lambda times the partial of g with respect to x. To find the partial of g with respect to x, we differentiate y plus x squared minus 9 with respect to x, treating y as a constant, which gives us 0 plus 2x minus 0, or just 2x. The next equation is the partial of f with respect to y equals lambda times the partial of g with respect to y. To find the partial of f with respect to y, we differentiate xy with respect to y, treating x as a constant, which gives us x times 1, or x, equals lambda times, to find the partial of g with respect to y, we differentiate y plus x squared minus 9 with respect to y, treating x as a constant, which gives us 1 plus 0 minus 0, or just 1. The third equation of the system is g of x comma y equals 0, which is y plus x squared minus 9 equals 0. To begin solving the system, let's go ahead and solve these first two equations for lambda. For the first equation, we would divide both sides by 2x, where lambda is equal to y divided by 2x. And for the second equation, we have lambda equals x. Notice both equations are solved for lambda, which means y divided by 2x must equal x. Let's go and take a look at that equation. Again, if lambda equals y divided by 2x, and lambda is also equal to x, we can say y divided by 2x is equal to x. And now let's go ahead and solve this equation for y by multiplying both sides by 2x. Simplifying, we have y equals 2x squared. And notice we have a y in our third equation. We have y plus x squared minus 9 equals 0. So now if we substitute 2x squared for y, we will have one equation with one variable that we can solve for x. So performing the substitution, we would have 2x squared plus x squared. Let's go ahead and add 9 to both sides, giving us equals 9. Combining like terms, we have 3x squared equals 9. Dividing both sides by 3, we have x squared is equal to 3. And now we take the square root of both sides of the equation, and we are going to have two solutions, a positive and negative solution. We have x equals plus or minus the square root of 3. Now that we know the values of x, we can determine lambda, since lambda is equal to x, as well as y. And we are going to have 2 points. Let's go ahead and start writing these out. One point is going to have an x-coordinate of positive square root of 3, and the second point is going to have an x-coordinate of negative square root of 3. And again, because lambda is equal to x, we know lambda is also equal to plus or minus square root of 3. So when x is positive, lambda is positive. When x is negative, lambda is negative. And now let's determine y using this first equation here. Y is equal to lambda times 2x. So we have y equals, let's use positive square root 3 first. We have square root 3 times 2 square root 3. Well, square root 3 times square root 3 is 3. This part is equal to 6. So when x is positive square root 3, y is 6. And now let's find y when x is negative square root 3, and so is lambda. We have y equals a negative square root 3 times 2 times negative square root 3, or negative 2 square root 3, which is also equal to positive 6. So the second point, when x is negative square root 3, y is also positive 6. And now we need to find the z-coordinates, or the function values, when x is square root 3 and y is 6, as well as when x is negative square root 3 and y is 6. And since the function is f of x comma y equals x times y, the z-coordinate for this point is just square root 3 times 6, or 6 square root 3. And for this point, we have negative 6 square root 3. So obviously the larger function value is 6 square root 3, and the least function value is negative 6 square root 3. So the first point represents the relative maximum, where the location is often given by the ordered pair x comma y, and the function value, or z-coordinate, in this case is the relative max. And for the second point, the location is given by negative square root 3 comma 6, and the relative minimum function value is negative 6 square root 3. And let's go ahead and verify this graphically. F of x comma y is the graph of the surface, and then the space curve is the intersection of the constraint and the surface. And notice how the 2 points that we found, one is a relative high point, or a local maximum here, and the point down here is a relative or local minimum. Verifying our work is correct, we did find the relative extrema. Also notice how the space curve does go up indefinitely as well as down indefinitely, which is why we have relative extrema here, not absolute extrema. I hope you found this helpful.